Two classes left.
That's insane.
I know. Counting this class. Sorry, Thursday's our last day. Just some final exam info, in case you forgot. Finals in this classroom at 1 p.m. on Monday, December 19th. It's open book, open note. That includes online materials. So if you take your notes online, you want to use Canvas, HECT, whatever, you can use it. It'll be one multi-part question. I may add something fun to the end as well. I haven't decided yet. But it'll just be one question for the most part on kinetics. And I will bring candy.
What kind of candy?
Well, that's up to you.
Can we make requests?
Yeah, what's your request?
Sour Patch.
Okay, I can do that. I can do Sour Patch. I was going to bring High Chews. Does anyone like High Chews?
Yes.
And I'll try to find some chocolate for the weirdos that like chocolate. I have Dum Dums as well. I'll bring Dum Dums. Dum Dums, High Chew, Sour Patch, and chocolate. Yeah. Yeah, sure, Lucy. Yes, I will probably do that tomorrow or Thursday. Sometime soon. It'll be posted. And I'll post the last year's exam as well. I will not stop you from bringing alcohol into the room.
Today and Thursday.
I would provide my own, but that's kind of fishy, so I haven't decided if I'm going to do it. Maybe next year.
Will you take a shot with me if I bring you one?
Yeah. Yeah, I will.
He was thinking about it for a second. He was counting 3.
Okay.
She's just going to have to bring a hammer.
Are we thinking Tina's or Jose Cuervo?
Jose.
Jose, okay.
Yeah, if given the choice, I'm always going to pick tequila.
Understandable.
So. Okay, so let's grind through some kinetics today. Just got 2 lectures left, and I want to kind of get through. We just don't have a lot of time to do that much, so I'm going to do my best. Today we're going to talk, and actually on Thursday too, we'll talk about this as well. We'll continue our discussion. We're going to talk about reaction rate laws today. So I want to talk a little bit about the different types of rate laws. I've used some terms, and we've a rate law, again, let's just recall again, our rate constant. Case of R is defined as, right, the collisional term A times e to the activation energy over RT. Right, and then we can draw a simple diagram for this. Here's our reactants. If we're going to do A to P, our reactants A to products P. Here's what they are in energy versus coordinate. They, of course, have an energy difference, delta G naught, between A and P. That tells you that sets your equilibrium. And our activation energy is this difference. Right? And the rate constant, right? The units of rate are proportional to per mole. Mole per liter per second. Right? So it's basically how much concentration can you build up per second of products. Right? So you can think of this as molar per second. Right? Or of course you can convert molar to anything you want. But this gives us concentration per second, right? How much does the concentration of your products build up as a unit of time? All right, and then we can write what we call a rate law, which is that the time derivative of the concentration of the products is equal to the rate times some function of concentrations. Okay, and we'll talk a little bit about what this rate law is and how to define them. So for instance, if A is a single molecule, and we have A to P, right? A decomposes into products, then dP dt is the rate times the concentration of A. Or if we have 2 moles of A react to form P, then the rate of the product formation is going to be equal to the square of the reaction of the reactants. Right? In general, for a reaction where you have stoichiometric coefficient mu A times nu B times B goes to products. Right? These are the stoichiometric coefficients. Then dp dt is equal to the rate of this reaction times the concentration of the reactants to their stoichiometric power, and so on and so forth. Okay, so what this says is that involved, for instance here, involved in the reaction to form products at 2A to P, you have 2 moles of A interacting to form P, right? So you square it. Right, but we're going to learn something, and we're going to come across examples where this fails, is that the concentrations or reactants involved in the rate law are those participating in the transition state of the rate determining step, which is the slowest step, or the one with the highest activation energy. As we'll see, some reactions have multiple steps to go from to reactants to products. And the thing that determines the kinetics is, of course, the slowest step. We call that the rate determining step, which is the slowest step. And of course, that also means the highest activation energy. But it's not the reactants that you put in, but rather the material that goes into the transition state here, right? Which molecules are involved here, right? And I'm going to show you an example where you would think that you would. Well, let's just do it really quickly. So here's my example. Example 1. Let's look at an SN2 reaction, the same one that we looked at a long time ago, CH3Br plus OH minus goes to CH3OH plus Br minus. Right, we showed that the reaction coordinate for this looks like this. Again, it's just a classic single transition state. We have bromine over here. And the transition state for this, if we draw it, looks like halfway between methanol, and methyl bromide. This is the transition state. Right, so what molecules are involved in the transition state here? Well, the transition state involves 1 mole equivalent of CH3Br, right? There's a CH3Br in there, and 1 mole equivalent of OH. Right, so every reaction involves, the rate determining step involves a mole of each reactant. So the rate law for this, the formation of methanol with respect to time, is the rate times the concentrations of the materials in the transition state. So that would be CHBr and OH. Note that this rate law has units of concentration squared. Right? It's dependent on 2 factors of concentration. So we call this a second order reaction. Right? Because there's 2, concentration is squared. Okay. Right? And that's why it's SN2. This is a nucleophilic substitution second order. Right? So when you see second order, first order, that tells you the order of the units of concentration in your rate law. And of course we include both of them because they're both included in the transition state. The transition state depends on the OH and the CH3Br concentration. Now let me show you a counterexample. Let's do another type of nucleophilic substitution. Let's take T-butylbromide and react it with OH to make T-butyl alcohol. I don't have enough place to draw it, but bear with me. Okay, like this. Now this is an SN1 reaction. And the reason why is because the OH can't, just as a reminder from back in the day, organic chemistry, the reason why this is an SN2 is because it's too sterically hindered behind the carbon for the OH to attack. You can't do this back attack, so SN2 doesn't work. So instead what SN1 is you take your alkyl halide and you ionize it to form the carbocation plus the bromine counteranion, and then the OH attacks from the front to then form our alcohol. All right, so this mechanism is slightly different. Okay? All right, so this happens in a concerted way. You form the bond, the COH bond as you break the Br bond, but in SN1 reaction, they happen in two different steps. You break the CBr bond, and then the OH comes in and attacks using an ion-ion reaction. The reaction coordinate for this looks a little different. So here's our starting materials, here's our products. I'll just write P and S for starting materials and products. There's a big transition state for the ionization, and then you form the carbocation. So this is CH3 3C plus Br minus. And then there's a smaller barrier where the OH comes in. So OH here, OH attacks. Okay, so the slowest step of this process is the ionization of the alkyl halide into the carbocation. So the transition state of the highest activation barrier, which is this one, this structure looks like, I'll just draw it here in the corner, looks like this. Where that carbon-bromine bond is slowly breaking apart, and you have a partial negative charge forming on the bromine and a partial positive charge forming on the carbon. So the transition state, the rate determining step of this reaction is the ionization of the alkyl halide. So that means then the only thing that's involved in the rate determining step is the alkyl halide. The OH doesn't come into play at all. All the OH does is sit around until there's a carbocation, and then you have a minus nucleophile, negatively charged nucleophile attacking a positively charged carbon. That's a very energetically downhill and low barrier process, right? Like opposites attract. So the OHC, the carbocation plus OH attack addition, the second step, is very downhill and doesn't have much of a barrier at all. So what determines the barrier is the ionization of the alkyl halide. So for SN1, the formation of our products, T-butyl alcohol with respect to time, again, is just dependent on the concentrations of the material in the transition state, which is just our starting material, and not the OH, because the OH is not involved in the transition state. All right, so this is what we call a first-ordered reaction, because the reaction rate is dependent on one order of concentration. Right, so if you look at these reactions in terms of the formula, right, we take an alkyl halide, we have a nucleophile, and we swap the leaving groups. We're doing the exact same thing here, but these have two different mechanisms, and therefore they have two different rate laws. Right, so even though the point that I want to take home is that the reactants in your chemical equation for a reaction do not necessarily define the rate law. We know that they're involved somehow, but how they're involved depends on the transition state. The rate law reflects the molar quantities of the TS, the transition state, not the starting materials. All right, next class we'll come back to this idea and we'll look at another reaction that we would expect is second order overall, and in fact it has an insane rate, which is very different than you would expect. And that's because the transition state of the reaction looks very different than the starting materials. Okay, so you can't always just look at a reaction and say, okay, I can write down the rate law, it's this. It's not necessarily going to be that because what determines it is the structure of the transition state, the structure of the rate determining step, or the transition state at the rate determining step. Right? So that's the classic differences SN1 and SN2. One is bimolecular, and the other one's unimolecular. Okay. And the chemistry of our alkyl halides determines that. I know that's a lot at once. Any questions about that?
Can you draw the transition state, the part in blue, a little
Yeah, sure. So I'm going to draw it. I'm just going to draw a big one right there. So there we go. The transition state of this reaction. Let me draw it properly since I'm drawing a big H3C, CH3, CH3, ... bromine, partial negative charge, partial positive charge. Like that. Right? The molecule dissociates by itself first, and then the hydroxyl comes in and reacts with it. Whereas in the SN2 reaction, they occur at the same time at the transition state. So the problem then is that it's not always, if you were given a reaction, an equation, it's not always clear what the kinetics are. But there are ways to tell. So let's do a classic way to tell. Let's, for instance, look at the reaction of Rx, an alkyl halide, plus a nucleophile. Just a general SN2 or SN1 reaction. R nuke plus X minus. Now, how do we determine the kinetics of this reaction, the rate law? Well, a really easy way to do it is this, let's do a concentration measurement. So we'll start with our starting materials. I'm going to write a table here. And then we're going to look at the observed rate and the prediction for SN2 and the prediction for SN1. Okay, so we're gonna let's start for instance with 1 mole of each and measure the rate of the reaction, and we see that K observed, or so let's change this to dr nuke dt, and then our predictions for it. Let's say the rate when you have 1 mole of each is 1, is standard rate. And now let's double the concentrations of each separately and ask ourselves, how does the rate change as we change the concentrations relative to 1? So if this were SN2, in SN2 our reaction rate is dependent on the concentrations of both starting materials. So we double the amount of starting material of one of them and not the other one. So this rate should double, right, because we've doubled one of them. This one should also double because it's dependent on both. Or sorry, let me change this over here to SN2. 1, 2, and 2. These are what we predict. SN1 is going to again have 1 here. SN1 is only dependent on the alkyl halide concentration, so when we double it, the rate doubles. But when you double the nucleophile, it doesn't change, right? So we already can tell the difference between the two, right? So if we observe a rate that looks like this, 1, 2, 2 like this, then we know we have SN2 because the reaction rate is dependent on the concentration of the nucleophile. Likewise, if we put 2 here on both, SN2 should have 4 times the rate because it's 2 times 2, but you should only get twice the rate for SN1 because it's only dependent on one of them, right? And so on and so forth. So if we see 4 here, we know the reaction's SN2, right? We see concentration dependence for both materials. So this is how we determine these rate laws, right? We just look at, we fix the temperature, and vary concentration. And this allows us to determine the rate law, or at least the proportions of concentration in the rate law, right? So this is the classic way that we do that. And if we're curious about the activation energy, so to measure EA, we do the same experiment, but vary temperature. Right? Vary temperature. And the reason why we vary temperature is because of the Arrhenius equation, right? It says the Arrhenius equation says that the log of the rate is minus EA over R times 1 over T plus the log of A, right? So we can, as we modulate T, we can measure the rate as a function of temperature, and the slope of that curve will give us the activation energy, right? So any sort of kinetics, if you go into mechanistic studies, right? If you look at reactions in organic chemistry or inorganic chemistry, and you ask, well, how do they figure out these rate laws? Right? This is exactly how they do it. They figure out the rate law, the proportions of the rate of formation as a function of the concentrations, by doing this concentration measurement. Right? Fix one and float the other, or vice versa, and do relative rates. And then to measure the thermodynamic quantities, right, the activation energy, you can do Arrhenius equation and measure it at various temperatures to get E sub A. Okay. So any sort of reaction kinetics, physical organic chemistry paper that does kinetics does this kind of measurement all the time. Super common. Okay. You've probably seen this already before, but the important thing is that I want to take home, this is the physical chemistry perspective, is that the rate law and the kinetics are not determined by the starting materials. They're determined by the transition state, the barrier of the reaction. That ultimately sets the kinetics, structurally, thermodynamically, kinetically, you name it. Right? We have to understand what's going on at the transition state to understand the reaction. That determines everything. Okay. That's about all I have to say about just general rate law rules. I want to talk about each case of rate laws now. All right. We'll start with zeroth order and first order reactions today, ones that have linear dependence on concentration and ones that have no dependence on concentration. And next class we'll do bimolecular second order reactions. So the simplest kind of, ironically, it's not actually that simple. The zeroth case is what's called a zeroth order reaction. And this is a reaction, say, A to P, where dP dt, rate of formation of products, is just equal to a number. No concentration dependence. So no concentration dependence. So this means that no matter what you do, the reaction occurs at the same rate at a given temperature. So rate is constant, is concentration independent. At constant T. Okay? This doesn't seem that interesting, but in fact, it is somewhat interesting because it can be a diagnostic tool about your mechanism. In general, zeroth order is an exception, not a rule, and typically occurs as a limiting case. It occurs at some limit. And I want to give you an example of a limiting case where you see second zeroth order reactions. So let's imagine that we have a metal surface here, a magic catalytic surface. All right, so this is some catalyst. This is a terrible marker. And on this catalyst, there's a number of free sites where molecules can bind. So I'm going to draw them in multicolor here. Imagine these are places that molecules can bind. Right? So these are binding pockets. Right? And let's imagine that this catalyst takes in NH3, 2 moles of NH3 gas, and outputs 3 moles of H2 plus a mole of N2. Okay, so reverse Haber-Bosch. All right, instead of converting nitrogen, hydrogen to ammonia, we're doing the opposite. Okay, in order for this reaction to occur, you have to stick, each binding pocket has 2 ammonias on it. Has to have 2 ammonias. Right, so each binding site can fit 2 equivalents of NH3, okay? And there's only so many, right? Because it's a finite surface, so there's only so many spots. Okay, so what happens is that ammonia comes in. There must be some rate for the ammonia to attach. All right, so the first rate, let's call this K sub S, the sticking rate. Chemists call this adsorption, not absorption, but adsorption with a D. Right? And so the rate of NH3 coming in as a gas and sticking to the surface is K sub S. Right? So the rate of this is K sub S. All right? And then there's going to be some rate the reaction has to occur, and then you lose it. All right? So let's let Kd equal the desorption rate, which is how long it takes to unstick, plus reaction. Okay, so it's a sum of the two. So basically there's 2 rates. There's a sticking rate, and then there's a processing rate, the input and the output. Okay, so let's look at we have a couple of cases here. It doesn't matter what the numbers are, but rather what are the proportions of the 2 rates. So first is that if the sticking rate is faster than the desorption rate, so let's make them much faster. All right, so basically, the system can stick ammonia on immediately, but it takes a long time for it to react and leave. All right, so sticking fast, reaction slow. So what happens as we increase the concentration of NH3? So what's going to happen is, we're going to measure the formation. We're going to measure the output, which is the concentration of N2, right? Because that's what comes out as a function of time. And so if we don't have a lot of ammonia in, then we don't generate a lot of N2. Let me think about this. Actually, let me change this a little bit. Let's change this to, the rate total, the total rate of the system as a function of input ammonia. Okay. So as we start to put more ammonia into the system, more of the spots, the binding pockets, get filled up with ammonia. Each one is allowed to act independently. So the rate will increase as NH3 squared because you take 2 NH3s in. So it's going to look like this. But eventually your ammonia but it takes a long time for the ammonias to come off. So imagine that you flood the system with ammonia. I'm just going to put N's for all these, and we fill up all the spots. All right, so now the catalyst surface is completely filled. And now you have another set of ammonia molecules coming in. And they're like, well, what the hell do I do? There's nowhere to go. Because it takes a long time for them to leave, right? This processing is slow. So eventually, the ammonia has to wait in queue, right? There has to wait in line. Once there's so much ammonia that all the spots get filled at once, then you got to wait for a spot to open so all the ammonia stays here. That means the rate's going to level off. Right? There's some critical amount of ammonia. Right? This is the saturation point where the catalyst has been saturated. And look, so as a function of ammonia, so once you get to this point where it's saturated, right, like right here, this is unsat, and this is saturated. Once you get to the saturated point, the rate has no dependence on NH3 at all, because there's no more place to put NH3. It just has to wait in line. So the reaction here in the unsaturated region is proportional to NH3 squared. It's second order. But in the saturated region, it's proportional to NH3 to the 0, which is 1. Right? So this is 0th order. Okay, so 0th order kinetics occur in catalytic situations or surface situations where you can flood a surface and have it stick, but it takes a long time to process. Okay? And so when you have too much ammonia, then the whole surface can't do anything. It's all out of spaces. It's completely filled up. All the registers have been taken, so you have to wait in line. No matter how long you make the line, the rate of the cashiers aren't going to take it. It's not going to go any faster. So the rate levels off, and you become 0th order. Right? So as NH3 grows, rate becomes 0th order. Right? So you often see this, for instance, in enzyme kinetics or medicinal kinetics. For instance, if you have a receptor, we'll talk about enzyme catalysis hopefully next class, if we have time. Let's say you're supplying it with some medication, right, at some concentration, and the receptor has some kinetics with that thing that you're binding it with, your medicine. And eventually, if you overdose on the medicine, you have so much medicine, all of that medicine is going to be sitting in your bloodstream. It's not going to be binding to your receptors at all because all the receptors have been taken. And so the rate of the inhibition, or whatever process you're trying to invoke in your receptor, doesn't occur any more quickly because all the receptors are taken, and so it's not dependent on the concentration of the medicine. Right, so the saturation point can play a big role, and is one of the reasons why overdosing occurs is because your body can't metabolize any faster as you start to bump up the amount of drug in your system, because there aren't any proteins or receptors or enzymes left to metabolize your drug anymore. And so then other things start to happen, right? Other side reactions and other things that you don't want your medicine to do start to happen because it's going to do the laziest thing. So if the choice is that for your drug is to either bind to the receptor and do what you want it to do, or run through your GI tract and destroy you, and your receptors are all filled up, well, it's just going to go do the next easiest thing, which is just to go into your GI tract and kill you. So 0th order kinetics play a big role in that case, right? Where the response of your medicine starts to level off as a function of concentration because there's no places to receive that medication anymore in your body as a function of time, right? It's like when Walmart only opens 5 registers on Black Friday. It's still going to take you 3 hours to get through there because no matter what you do, the rate of cashiers is never going to increase. Okay, so there are two other cases, right? The other case again is where the desorption rate is faster than the sticking rate. Here, that means then that every time that sticking's really slow, but desorption basically it just comes off instantaneously, right? The moment an ammonia comes in, it just leaves. Right? Here, your system is always second order. Because oh wait, no, it's not. Sorry, hold on a second. Absorption is faster, and so the sticking is slow. Yeah, it's always second order. Sorry, it's always second order, right? Because every time you get one on, it just comes immediately off, so you can constantly fill them in. And then the other one is where they're equivalent or close to each other. And here you have competition. Right here, the rate ends up being the sticking rate times ammonia squared. Right? They're about the same. Then you can stick them on at second order. But you also have to consider how many sites you have. If they're roughly the same rate, then you've got to make sure you have enough sites to stick all the ammonia that's coming on. So this rate ends up being also proportional to the rate, the concentration of binding sites. Like that. All right, so it's a sum of two rates. Right? The more binding sites you have, the more ammonia you can stick in. If you have a small amount of binding sites, then this reaction is never going to go much faster because there aren't any sites for it, right? So this is not ideal. And typically, this means need more catalyst loading. You don't have enough catalyst. Ideally, what you want is enough catalyst to support the amount of material that you have. So if the desorption rate and the sticking rate are about the same, then that probably means you need to put more catalyst in your system so that you have an excess of places for ammonia to go. So your rate will increase as you increase ammonia. Okay, so we'll look at this in terms of enzymes hopefully on Thursday, and that will become more clear how the zeroth order can compete with other types of ordered kinetics. Okay. The next type of reaction I want to talk about for the rest of the class are first order reactions. These are really interesting. Maybe not as interesting as second order, but it depends on who you ask. So here the kinetics are proportional to one unit of concentration for A to P, for the reaction A to P. I am going to change this a little bit. For every mole of A reacting, P forms, right? They're 1 to 1. So I'm going to rewrite this instead as, this means then that the formation of products is equal to the opposite of the depletion of starting materials. Okay, the rates are they're related, and they're just negatives of each other, right? P and A form and deform or destroy at the same rate, so they're just equal and opposite to each other. So we can write the rate law as dA dt equals minus KRA. Okay, so it's a negative rate. This is the depletion rate, and we can solve this. We can solve for T and concentration and come up with a formula for this, an integrated rate law. The way we do that first we multiply both sides by dt. So we have dA equals minus kr times a times dt. And then we divide both sides by a. So now we're left with dA over a equals minus kr dt. Okay, and we can integrate this equation. All right, and so let's think about how we integrate this. So we have an integral of dA, the concentration, over the concentration, change concentration over concentration, equals the integral of negative kr dt. Then we have to integrate bounds. So I'm going to integrate from t equals 0 to some final time t. And so what's the concentration of A at t0? It's the initial concentration of A sub naught. And the final concentration is just A. Like that. All right, and when we integrate this, this ends up being the log of A minus the log of A naught equals minus kRt. Okay, K, rate constant is just a number, so it just comes out of the integral. We just did the integral of dt. Okay, and so this is equal to, just simplifying a little bit, is the log of A over A naught equals minus kRt. We'll take exponential to both sides, which is that A over A naught is equal to e to the minus kRt. Which means that the concentration of A as a function of time is the initial concentration times e to the minus kRt. Right? And we can write that in terms of the products. The product concentration as a function of time is the initial concentration of the reactants times 1 minus e to the minus kRt. Like that. So now we can measure, if we know, right, this is a really nice equation, because now what we can do is, if we can monitor the concentration of our products with respect to time, we have a model to fit it. It's going to be exponential, and it looks kind of like this. So again, let's look at what this looks like on a graph. So we're going to plot time versus concentration of P. All right, so what is the concentration of P at t equals 0? Well, we have e to the 0, which is 1. 1 minus 1 is 0, so P, of course, is 0. Obviously, we start with no react product, so obviously the concentration of P at t equals 0 is 0. And let's think about what it is at infinity. So here we have e to the minus infinity. That's 1. Right? It's e to the 0, which is, e to the minus, let me start over again. E to the minus infinity is 0. So you have 1 minus 0, which is 1. So it's A naught. So it's asymptotically goes to A naught. Of course, that means that you've converted all of your materials, starting materials, to products. And it kind of looks like this. This is a function of time. Right, so first order reactions have this exponential form. And it says that the log of the concentration of your products or your reactants versus time is a straight line. Okay. So if we were to take this as if we were instead to look at this as a function of log P, it would asymptotically approach log of A naught. Log of P goes to 0, goes to minus infinity. So it would look like this. something like that, where the rate, wait a second, hold on a second. Is that right? Yeah. It increases like this. It's a function of time in terms of logarithm. Okay. Anyway, I digress. The interesting thing about this is that we can calculate a half-life, or the time it takes to deplete 50% of your starting materials. Right, and the way that we do that, let's take this equation here. A equals A naught e to the minus KRT. Okay, and when we're halfway, this is going to be equal to 1/2 A naught, right? So we're left with 1/2 A naught is equal to A naught e to the minus KT. These go away, so we're left with 1/2 equals e to the minus KRT. All right, let's take the log of both sides. The log of 1/2 is equal to minus KRT. The log of 1/2 is the same as the log of 1 minus the log of 2. This is 0. It's KRT, which means that the log of 2 is equal to KRT, which means that the half-life is the log of 2 over KR. So this is the half-life for a first-order reaction. I'm sure you've seen this equation a million times, maybe not. But what it tells you is that the half-life of your material, if it decays first order, is independent of its concentration. Right? It just cools, it just decays at some constant rate proportional to 1 over your rate. What we're going to find for second-order reactions is that the half-life is actually dependent on concentration. So this is unique for first order. First order reactions always occur basically at the same. They don't care about the concentration at all. It's completely independent, the rate at which it occurs. That will be different for bimolecular reactions. So this is why you see half-life, for instance, for nuclear decay, right? Radiation, nuclear radiation. That's a unimolecular process or a unatomic process that occurs with just one atom decaying. And the rate of that, the half-life is going to be proportional to the rate of decay of the molecule, 1 over that, the rate of, or the nuclear decay of the atom. And so you see this equation all the time. And anything that's dependent on, any reaction that's dependent on just 1 mole of the starting materials is always going to have this behavior. All right. And you get the half-life is concentration independent. So it doesn't matter how much you have, but it just depends on the material or the process itself. Okay, and I'll show you next class that for second order reactions, that's not the case. Second order reactions have a half-life that's dependent on concentration. So the more you have, the slower, the faster something will decay. Questions? Cool. I want to teach a final lesson about first order reactions today. An application, if you will. And it kind of goes into this story that you can't always trust your reaction formula to determine your kinetics. And the case I want to look at are unimolecular reactions. Reactions that occur with just 1 molecule. Okay, so the idea is a molecule decomposing on its own. So a great example, for instance, is, we talked about this last time, or one time. So you take acrylonitrile and heat it, or shine a laser at it. You form acetylene and HCN, for instance. There are other products as well. But This reaction just occurs on its own, right? You take one molecule and you break it into multiple parts. Okay? So this is the most common type of first-order reaction, or very commonly studied type of first-order reaction in chemistry, is what happens to a single molecule when it breaks down in a unimolecular way. And so let's look at the reaction diagram for such a process. Again, we'll just draw the same reaction coordinate diagram that I've always drawn. Here's our starting materials. We have an activation energy. Well, let's say, for instance, that it's downhill. Okay, so this is our activation energy. And this is delta G sub 0. All right, same reaction as always. In order for this reaction to occur, now what we talked about, all right, so let me start over again. When we talked about last class about collisions, we talked about, well, one of the ways that molecules can react is to collide together, right? And they transfer energy through the collision, and that provides enough energy for the reactants to get over the barrier, right? This collisional reaction. But if you have a unimolecular reaction, what is it there to collide with? Right? There's nothing to collide with. It's not a bimolecular reaction, it's a unimolecular reaction. So here's, for instance, let me draw in green here, the critical energy that the system needs to be at. It's right here. We'll call that E, well, it's E sub A. All right? Your A needs to be up this high in order to get over the barrier, classically. Right? So we need to find some way to excite the molecule energetically to get it up over this barrier, but we don't have any collisions to make. Right? This is a unimolecular process. As far as we know, there's only one molecule involved in this. There aren't any collision partners, theoretically. All right, so what I'm going to say is that we're going to thermally activate the molecule somehow with some energy to call it A star. Okay, so imagine A to A star is some energetic process that excites the energy of A high enough so that it can react. We'll also define a P star here, so that eventually it'll have to come back down to P. Okay? So the question is how does this happen? Right? So we know we can go monitor, we can go do this reaction and do the kinetics. And what we find is that the rate of formation of HCN, dt, is proportional to the rate times the concentration of our starting material in first order. Well, how can that be? How can this molecule generate enough energy to get over this barrier without another collision partner, right? There's no partner here, right? It's not two, right? There's no collision partner occurring here. It's just a single unimolecular reaction. So somehow this molecule has magically got enough energy to come. So one way that it can do that is through absorption. How to get energy. So one classic way to do that is absorption of thermal radiation. So what if we do this instead? What if we put our molecule in a reactor? So here's our reactor. It's just a flow tube. And on the outside of it, we put heat coils or heat tape to heat the system up. Okay? So we heat the reactor to give it some hot energy. And through here we flow our molecule A. A comes in through here, it heats up. A goes to A star because of the heat. It absorbs radiation heat from the chamber or the reactor, and then eventually becomes product, right, through heat. So drive reaction through heat? Well, first of all, the problem is that if the activation energy is on the order of 100 kilojoules per mole, T needs to be over 5,000 degrees, roughly. I think it's 3,000, right? It needs to be really hot. So 3,000 degrees gives you roughly about 100 kilojoules per mole, give or take. So you need to get it really hot. But what's worse is that doing work through heat is not efficient. Right? Some of that heat is lost to entropy. So in order to heat molecules to 3,000 Kelvin, our heater must be hotter. Right? Some of that heat is going to some of that heat's going to radiate and it's just going to be lost to entropy, right? So you don't get to use all of it for work. So in order to get these to 3,000, we need to get the chamber to even hotter, right? The reactor needs to be even hotter than that. But here's another problem. If we cause A to become A star through heating, due to energy conservation, all A star does is go to P star, right? It goes from here to here, right? No energy is lost. So we have thermally excited P. Therefore, to form P, to form regular P, we need to cool P star. So P star to P requires emission of radiation by P star and absorption by the reactor, right? You need to have something to radiate and absorb the heat. But here's the problem. Imagine that we have P star in here. And you want to cool it so that now it forms P. But the temperature of P star is less than the temperature of the reactor, right? We said we had to heat the reactor higher. So it's like 5,000 Kelvin and P star is 3,000 Kelvin. So no heat transfer occurs from P star to the walls because the walls are hotter. Okay, so in order to actually do this reaction in a reactor, you have to do it differently. First, we need, so let's try a different experiment. So here's our hot reactor. So here's our coils. So set these to T equals 5,000 Kelvin, roughly. So it's a huge number. And that's thermally efficient enough to get our temperature inside to 3,000 Kelvin. Okay? And so what happens when our molecules now flow through here? So we'll have the A's come in. A goes to A star. And that isomerizes or changes the P star, right? The thermal energy allows us to do that. And then what we have to do is transport P star into a different region of our instrument that's colder. So here we'll put cooling coils, or 298, for instance. So now as the P stars, the hot P starts to diffuse through this boundary. P star is initially at 3000 Kelvin, and then eventually it starts to cool and radiate out until you form P at 298 Kelvin, right? So you need a hot region that's hotter than the temperature you want, and then in order to stabilize P, you've got to immediately cool them, so heat transfer is efficient. Okay, so this is what people thought for a long time. This is the way to do unimolecular reactions. Heat the bejesus out of them until they have enough energy to react, and then stabilize the products by cooling them out. Right? This works. It does work. But what this predicts that unimolecular rates are dependent on the absorption efficiency of the walls of the reactor, the reactor walls. Okay, so if you have, for instance, the idea is that rate is proportional to the surface area of the reactor. Right? The more surface area there is of the cool reactor to absorb heat, the more efficient the reaction should go. The faster you'll form P. But experiments show unimolecular rates have no dependence on reactor surface area. So this thermal activation mechanism, this idea that you heat your molecules up so they have enough energy to react and cool the products to stabilize them, predicts that your rate's dependent on the surface area of your reactor, how efficient it is at heating and cooling, absorbing radiation or emitting radiation, but applied the rate's dependent on the surface area, and it's not. It has no dependence on it. You can make the most amazing reactor super efficient, and it's not going to change the rates of your unimolecular reactions. Oh, I'm sorry, Lucy.
No, you're good.
So that's a problem, right? So for years in the early 20th century, that's how people thought these things work, right? They see these unimolecular rates, they know that molecules decay, and they said, well, what must happen is the only thing that's possible is that you absorb thermal radiation from the exterior, either from heat or from light, or from some radiative source that excites your molecules thermally. If you get them hot enough, they have enough energy to get over the barrier. And then as you start to cool them, and the products, the P stars, they stabilize and form P. Right? So you go up in energy here. This is the heating. This is heat. This is reaction, and this is cooling. Right? You just do a loop like that, right? And so people thought that's the way things work, but that again leads to this rate dependence on the efficiency of heat absorption or heat emission by your reactor, which is surface area dependent, and they don't have any relationship to surface area at all. It does not matter. So this doesn't work. Before I erase that, sorry, I'm gonna come over here. Okay, so what happens then? And it turns out, we'll start this today and finish it up next class, is that the big insight is that unimolecular reactions are driven by two-body collisions. You need a collision partner to get your energy up high enough to activate A to convert to P. That has no dependence on surface area, it depends on concentration. Right? And as we'll see, concentration is the key factor. So in fact, what drives unimolecular reactions is collisions. So A to A star requires an activating inelastic collision with some partner. A star to P star occurs spontaneously or at equilibrium. And P star to P either requires another collision or emission of radiation. So P star can actually cool to P by emitting a light, by emitting a photon. Right? We won't talk about that too much, but that is an important thing, is that you can stabilize your products by having them emit light, which is the way they remove energy. We'll learn a lot about that next semester. But in order to activate the system, you can't do the inverse. And the idea is that absorbing heat radiation to drive A to A star is not efficient and doesn't work very well. So the only way to efficiently get energy is by inelastic collisions, right? We have a collision that transfers energy from one partner to the other. So we can kind of write the mechanism of this very simply. The first step, collisional activation, that's where we take A and react it with some molecule M. It could be another A. Let's just say it's another A. And they transfer energy so that one of them gets activated. Right? So they collide and they transfer energy with each other. Okay. Second step is the reaction itself. Let's call the rate for the first step K sub A. Or let's call it K sub 1. Second step is the reaction itself. That's going to be A star to P star. We'll call this K2. This is going to be fast because it's already over the barrier, so it isomerizes very quickly. That tends to be a very fast reaction. And the third step is deactivation or cooling or relaxing, or well, let's say cooling of products. So that would either be P star reacts with another molecule of A to form P plus A star. We'll call this K3. Or it could be that P star emits a photon, emits light, to form P plus light. This also has a rate. You can calculate the rate of this with quantum mechanics. So we'll call this, I don't know what we want to call it. We'll call it, it's actually called the Einstein coefficient. We'll call it K Einstein. Right, there's some rate for it to emit a photon as well. So there's a couple different ways for it to do it. But the important part is that and you can't represent the kinetics of a unimolecular reaction. You can't get an accurate model of what actually occurs in an experiment without considering that the reaction requires an initial two-body reaction. That a unimolecular reaction is in fact a bimolecular reaction. Right, this is called the, we'll look at it more carefully next class, but this is called the Lindemann-Hinshelwood mechanism. All right, we'll look at it more carefully next class. We'll do an example, we'll work out the kinetics and stuff, but I just kind of want to talk about the initial part. The take-home point is that unimolecular reactions are actually bimolecular reactions. And in fact, bimolecular reactions also require a stabilizing third body. For the same reason. We'll look at that a little more carefully next class. So for instance, in the liquid phase, in the solution phase, or almost done, solution phase, this isn't a problem. Because solvent is an effective partner for energy transfer, right? There's always a solvent molecule to collide with. All right, so we don't typically worry about these things in the liquid phase because in the solution phase, because there's always a solvent, right? There's so much more solvent, the concentrations, the number densities are very high. It's very easy to do a collision, right? It's very easy to collisionally stabilize in the solution phase. But in the gas phase, you don't have that luxury. So in the gas phase, unimolecular and bimolecular reactions can be extremely slow or even impossible at low pressures because there aren't that many collision partners. It takes a long time for a collision to occur, much less one that's inelastic. So in the gas phase, this becomes a big issue. In the gas phase, that's why typically we think about reactions in the gas phase not being very efficient or very fast. Right? In solution phase, we can react anything with anything. But in the gas phase, it's much harder because you need to be able to stabilize your products energetically and trap them in the low energy form, which requires collisions. For instance, getting two atoms or two molecules to collide with each other in the right way in the gas phase is tough. It can be anywhere from 3 to 6 orders of magnitude tougher to do 3-body reactions, to get a third body in the right position. Right? So bimolecular reactions are very, very hard to do in the gas phase because you need a third body. And this is a reference back to orbital mechanics. If you think about the planets, it's very easy to come up with a stable solution for 2 bodies to come together and to react with each other. It's much harder to find a stable solution for 3 bodies to come together. If anyone's ever read the 3-body problem, that Chinese sci-fi novel, they talk about this all the time. Right? The physics of 3 bodies coming together in a stable way is very difficult. It's also very rare, right? Because you not only need 1 collision, but you need 2 collisions. And so bimolecular reactions tend to occur very, very, very slowly in the gas phase because it's very rare to get 3 bodies in at the right time. Okay, so we'll dig through this a little deeper next class. This will allow us to talk about bimolecular reactions a little bit more, since we'll have to think about them, talk about unimolecular reactions, and then we'll finish off with a few more examples. One last thing, I just always make this spiel. Course evaluations are up on Canvas.
And LA ones.
And LA ones. Please do them if you can. I read every single comment that's sent to me. So your comments, not only are they helpful, but they'll also determine your fate next semester. If there's some change that you would like to see happen, or if you just like the way things are, if you just want to compliment me, or you just want to insult me, I really don't care. I take any and all comments, I read every single one, and I consider them. So please do fill it out. It means a lot to me. And if you want to see me here, my bosses also look at them too. So they if you want them to know that I'm a terrible teacher, that's a good way to do it. All right, see you Thursday.
All right, peace, Mike. Cypher.
Yeah.
You got marker on your face.
Oh, do I really?
Oh,
Oh, yeah.
I was waiting to let you know.
Yeah.
Wait, Dr. Cypher, Mike's wondering if you just leave it up for now.
What's that?
I just gotta finish writing it.
Oh, yeah, that's fine. Yeah, go right ahead.
Have a good day. Thank you, Jacob.
Let me check my face. Oh my God, it's just making it worse.
I was just gonna come up and tell you smurfed yourself.
It's on your
No.
forehead too, like above your
Not the
eyebrow.
All I got is a mask. So.
It's tough.
Have a good week.
Yeah, you too. Is that a little better?
Yeah, Wednesday.
Yeah.
All right, now I'm just red. What's up?
I was wondering, I don't know if you mentioned it, so I'm sorry if you did.
Yes, I actually
Is
do
the
have it.
finding cumulative or is everything